Hello, we're going to be talking about bridges today, so you want to make sure you have your notebook out, ready to take notes. Anything you see in red, that's what you want to copy down. I'll also let you know when there's a diagram I want you to copy down. So we're going to talk a little bit about bridge types. I'm going to start by going over a few important vocab words. Right, so span is just the distance between two bridge supports. The abutments are the supporting structures on either end of the bridge, so they can look a little different depending on the type of bridge. But the basic definition I want you to have down is it's a structure that supports the end of the bridge. Right, and then the girder is that main horizontal support that runs across the length of the bridge. Right, if you need to pause at any time, pause in order to get all the things you need down. The next thing I want you to write down is what a load is. And loads are the weight distributed across the bridge. So there's two main types. There's the live load, which are things that are dynamic. They're constantly changing. That could be wind, that could be an earthquake, that could be a car crossing the bridge, a person crossing the bridge. So anything that's a changing force that's going to act on that bridge. The dead load is just the combined weight of that entire bridge. So the bridge is under force of just its own weight. That's considered the dead load. Typically doesn't change unless you change the structure of the bridge. You add components to it or take away components. The dead load is typically going to stay the same. Alright, couple more words. Almost done. Compression. This is a force that shortens, it pushes together. Right? So bridges are often under compression in different parts. And then they're also under tension, a pulling force. Right? Most bridges experience both of these. Sometimes they can experience them both in the same section of the bridge. Alright, so a beam bridge is the first bridge we're going to talk about. It's a rigid horizontal structure that's resting on two piers, one on each side. These are the simple bridges that we tend to see most often. And you want to draw this diagram because it's a good one that shows the forces involved. You have the force of the load on top of the bridge, usually, let's say it's a car, right, pushing down. You also have the reaction force. Think Newton's third law, equal and opposite action reactions. So if there's a load pushing down, there's got to be a reaction force pushing up. And that causes a lot of compression on these piers. The top of the bridge is also going to be experiencing compression, while the bottom part of the bridge is going to be experiencing tension. And why is this? We can look at this. If we look at this sponge, this might help us kind of demonstrate this phenomenon. If, let's say my hands are the load and I'm going to push down, right, I'm pressing down onto the bridge. Notice the lines on the sponge, how the top layer are getting closer together, and the bottom, the lines seem to be spreading apart. It's this bending that causes compression on top, pressing, and stretching down below, tension. Right, so even just one beam of a bridge could be undergoing both at the same time. The top part has to be able to withstand compression, the bottom has to be able to withstand the pulling and the tension. So you need materials that can withstand both, typically, when you're making a bridge. Alright, so make sure you had that copied down. You're also going to want to copy down anything you see in red here. These are a couple of examples of beam bridges. So typically a beam bridge, its span can't really go over about 300 meters. If they have really strong reinforced materials, maybe they could get up to about 330. But typically not more than that. So here are a couple of examples of beam bridges here with spans that are a little on the high side. You're not going to see a beam bridge with a single span any bigger than that, really. You do find continuous span beam bridges, though, and that's several beam bridges that are linked together to cross a wide distance. So here's an example, the world's longest. It's over water, Lake Pontchartrain Bridge. Right? It spans 38.4 kilometers, the whole distance of the bridge. But within that, there are tiny spans that make up this entire distance. So it's like linking a bunch of beam bridges all together. Here's just a few more continuous span bridge examples. And it might be a good idea to look some of these up. It's always nice to see, especially in other parts of the world, the types of bridges that they have. Alright, so the next one we're going to talk about is a truss. And a truss really isn't a whole separate section or separate type of bridge. It's more of a structure on a bridge. So it's a supporting structure. The skeletal structure is made up of many small beams, and they're normally in the shape of triangles. So you'll often see them look like this. Again, pause at any time when you need to. Okay, so here's a diagram you're going to want to draw of a truss. Right, it shows the load pressing down on the bridge, right, the reaction force, the abutments on the side pushing up, so they're going to be under compression. And then you can see the alternating different types of compression and tension that are happening here. Right, so because there's force from the load pushing down, these vertical beams are going to be under compression. Right, there's force pushing down, and there's force pushing up, the reaction force. So they're under compression. The diagonal beams balance that compression out by creating tension, a pulling force that helps to balance out. Right, so you can see there's compression and tension balancing here. The truss helps to strengthen that bridge. Okay, make sure you get that diagram in there. All right, a cantilever is really a form of a beam or truss bridge. It's a fancy truss, basically. And it's a structure or beam that is unsupported at one end, but supported at the other. Think of it kind of like a diving board, right? So it's attached over on the side and it has support, and then it kind of juts out into the water, and it doesn't really need anything holding it up necessarily on the ends. And it'll often be like two diving boards coming out and meeting each other, and then you can rest the bridge on top of them. Alright, so here's just a good diagram of a cantilever bridge. And you can see it's a lot like the other truss that we saw, but it works a little differently because you have tension here, right, on the top beams. They're under tension because if there's a load on the bridge, it's pressing down, which is going to be pulling them and creating tension. As it's pressing down, it's going to be compressing these beams below, creating compression. Right? So you end up with compression, tension, they balance each other out, and they both provide support when you place the actual span in the middle. It provides support for that bridge. Alright, so make sure you draw that diagram. And you're welcome to use different colors to represent tension and compression. It's kind of helpful. Alright, typical spans for cantilever bridges, 40 meters to 500 meters. Because they're so supported, they can have a slightly larger span than just a regular beam bridge. Alright, this would be the world's longest here. Pont de Quebec. Right. You also might remember from the video we watched in class, the Firth of Forth Bridge. This word Firth is just another word that they use for a waterway, and it's the Forth Bridge. Constructed in 1890. This was really the first example of a cantilever. There's just some more pictures of it. Alright, next one we're going to look at is an arch bridge. An arch bridge is a semicircular structure with abutments. Those are on the side. Right, these would be the abutments here. On each end, the arch naturally brings the weight of the load from the roadway to the abutments. So because it's pressing down, it's going to be pushing out in these directions, compressing against the abutments. Okay, so you're going to want to draw a diagram of this. Here are the forces involved in an arch bridge. And really the arch bridge is a little different from other bridges because it mainly just experiences compression. A lot of the other bridges, it's about a balancing of tension and compression, but compression is really all that an arch bridge experiences. There might be a slight bit of tension near the abutments because they're going to be pushed out to the sides. There will be a little bit of pulling, but generally it's all compression here. Alright, typical span lengths for an arch bridge. About 40 to 150 meters, so they can get a little bit longer than the unsupported beam bridges, but not much. The world's longest is in China, and the longer they are, the more supports they need, really. You can see that there's a truss design in here, right? So the truss provides extra support. Here's the U.S.'s longest arch bridge, New River Gorge. You tend to see arch bridges a lot near gorges or places that naturally have big rock structures because that allows a lot of support for the abutments to build and helps with the compression forces. Alright, suspension bridges. The deck of the bridge is held up by cables. The main cables, which are the ones that run along the top, they're strung over usually 2 towers, and then there's vertical or hanging cables that connect to the main cable. The towers support most of the road's deck weight. The main cables have to be anchored though, so there's always anchorages on the side to help keep those main cables taut and under tension. Right, so you'll see the tension forces are all along each of the cables. They're being pulled. Compression happens on the towers. Right, they're holding on to this weight of the load. It's the reaction force from below creates compression. Right, so tension and compression is balanced out here. A few examples. Right, typical span length of a suspension. They can get to 1,000 meters, some of them 2,000 meters. They can be quite long. They're one of the really the longest bridges that we have in the world. Tend to be suspension bridges. The world's longest is the Akashi Kaiko Bridge in Japan, and that spans 3,911 meters. And just that little center span in the middle here is almost 2,000. Alright, so here's just a list if you're curious of some of the longest suspension bridges in the U.S. If you look by city, New York tends to have the most. You also see some in San Francisco. There's one in Delaware, Washington, but New York by far has everyone beat. Alright, cable-stayed bridges, they are a type of suspension bridge. They're a continuous beam with one or more towers built above piers. From these towers, cables stretch down diagonally and attach to the girder or support deck. So there's a difference here. There's no main cable that runs along the top with vertical cables. These run diagonally directly from the towers themselves. Right, so make sure you get a diagram here of the compression and tension. Compression is going to be against the towers. Tension is going to be the cables themselves or pulling. Right. There's really 2 forms that you'll see. There's the fan, which is when all of the cables come down from the top of the tower, and there's the harp, which they're coming down from different parts of the tower. So you might want to draw just what they look like so you know fan versus harp cable stayed bridge. Alright, a couple of examples and the typical span here. They don't get quite as long as other suspension bridges, but they can be quite long. So 1,000 meters or more. You see the total length here is 3,000. The center span is about 1,100 meters. So they get long, just they're not the longest, not like suspension bridges. Alright, so you want to make sure you go back and cover anything that you missed. That's about it for tonight. We'll talk more about bridges as we go. Have a great night.